in order to organize that streaming?
By INdAM.
It's by INdAM. That's very convenient. In order to organize that streaming.
Yes, the INdAM consider the possibility to transfer the Zoom meeting on
YouTube. In order to organize that streaming.
Yes. Yes, the INdAM.
Oh, someone has created a loop. It seems we can hear YouTube. As a loop.
Echo.
Yeah, we are doing this for this. I mean, to increase resonance of the workshop, we are doing it with echo.
Ah, Enrique, finally you are there.
Yes.
Yeah. I have to take a cab after your talk, but I'm. Yeah. So Emmanuel, so to increase the impact of the workshop, we are doing it with echo. So in the beginning, I mean, it takes, for the speakers, in the beginning, it's a bit, you have to get adapted, right?
Right.
Okay, so you are in your office, no? Is this your office, Emmanuel?
Yeah, I'm in the office, yes.
I'm glad you are here, Enrique. This image of you in the square looks like the big brother.
Yeah, I am in the square of Erlangen, although, in this moment, I'm not there, but I'm traveling today, but I'm glad. Oh, I see also Lucho, right?
Yes.
Okay, yeah.
Maybe.
Alessio also, people are fresh. Oh, Mauricio. So, yeah.
Yeah.
So, after fiesta all weekend, right? So, good.
Good. So maybe it's time to start, since most people are already attending, and we are about 3 minutes late, but that's affordable. So good morning to everybody, and welcome for this online session of the conference. I hope you will have a rewarding start of the week. And I must start with an apology. I shouldn't really be here as a chairman, since I already did my job last week in presence. But what to say? There is sort of a tradition. Every time I'm at a conference with the first speaker of today's session, I happen to be his chairman, and this could not be broken on this occasion. So I'm pleased to introduce Emmanuel Trelat from Paris, where he's at Sorbonne University, professor and director of the department of the Labo Jacques Lilians, and the president director of the Fondation des Sciences Mathématiques de Paris. Emmanuel is an expert in control theory, both finite dimensional and infinite dimensional, and sub-Riemannian geometry. And this includes also, his interest includes also numerical aspects and application, especially to aerospace sciences. The list of honors he has achieved is outstanding. Prix Maurice Audin in 2010, Felix Klein Prize by the European Mathematical Society in 2012, then Prix Blaise Pascal by the Society of the Industrial and Applied Mathematics in 2014, and then Grand Prix Madame Victor Nouri in 2016. And in addition to that, I must say he has exceptional communication skills, and I'm sure we'll appreciate in this talk, of which you see the title on the screen. Please, Emmanuel.
Wow. You know, Pierre Marco, there is also another tradition, and the tradition is that you be my chairman, and I can say you are really my best possible chairman. Thank you very much for this very nice introduction, Pierre-Marco, and thank you for the invitation. And I'm going to report on works that I have achieved and that are also still ongoing with Loïc Bourdin, who is at Université de Limoges in France. And the topic today is about the robustness property of controllability under control sampling. So let me introduce the framework. Throughout the talk, so we are in finite dimension. Throughout the talk, we consider a nonlinear control system given in the classical form x dot equal f of tx u, where x is the state evolving in Rn, u is the control that takes values in some subset capital U of Rm. Let's say that you are also given some initial and final point, and also a final time, a final horizon of time, capital T. Well, we will say throughout the talk that the point x1, the target point x1, is L infinite U reachable in time capital T from the initial point x0 whenever there exists a control U taking values in capital U, such that the corresponding trajectory of the control system starting at x0 reaches exactly the point x1 in time capital T. So this is usual reachability under the control constraint capital U. And our objective in this work is to determine whether this reachability property in fixed time t remains robust under control sampling. So let me explain what is control sampling. Sampling the control means that you are now given a partition of, oh, sorry. Let me stop it. Okay. You are now given a partition of the interval of time 0 capital T, so which is a partition, okay, with initial time 0 with final time capital T, or maybe you may be given a sequence of partitions with their norm that is defined here, which is tending to 0, maybe. And you define the set of piecewise constant controls over this partition. I will denote it by PCT of 0t with values in capital U. It means piecewise constant controls over this partition. And throughout the talk, we will say that x1 is PCTU reachable in time capital T from x0 whenever there exists such a control that is piecewise constant along the subdivision with values in capital U, such that the corresponding trajectory of the control system starting at x0 reaches exactly the point x1 in time capital T. This is control sampling. So the question is, we assume that a given target point x1 is L infinite U reachable in time t from x0. That means classically reachable with a classical measurable control. You are now also given a partition of 0t, and you wonder whether that point x1 is also PCTU reachable in time capital T from the point x0. So in other words, we wonder how robust is the property of reachability in fixed time under control sampling. Of course, a first obvious remark is that the norm of the partition should be sufficiently small, because otherwise the set of points that you can reach is purely discrete, right? It's an obvious remark. Also, a second remark, less obvious, is that if you do not do any specific assumption, then even for small values of the norm of the partition, the target point x1 may fail to be PCTU reachable from the point x0. And a very obvious, a very simple example is given here, where in this very simple 1D example, we take an initial point and a target point, so that for this very simple control system, there exists a unique control that steers the system from x0 to x1. And this unique control is, you see, u of t equal to t. So you immediately understand that as soon as you discretize the control over a given partition of time, since it was unique, then over a partition, you cannot reach x1 with piecewise control, piecewise constant controls. So it means that you need a sufficient assumption in order to ensure robustness. And this sufficient assumption is given here. This is the main result of a paper that is to appear in MCSS. These assumptions are almost sharp. I will soon comment about that. So the assumptions are, we assume that capital U, the set of values, the control constraint set is convex. We assume, of course, that x1 is reachable, classically reachable. And the third assumption, which is the main one that I will explain, is that we assume that U is so-called weakly U regular. And I will explain what it means in the next slides. Then under these assumptions, there exists a threshold, delta, so that for every partition of the interval of time of norm less than delta, then it is true that the target point x1 is reachable, is PCTU reachable in time exactly capital T from x0. And you can observe that that this property is stronger, obviously stronger than the property that is written below, that would say there exists a partition so that the target point x1 is PCTU reachable. Now, let me explain in the next slides what is the concept of weak U regularity of a control. So in order to explain that, I will make a recap in the next slides on, let's say, classical and not difficult reachability results. The first basic object that has to be introduced when you study reachability, accessibility, is the endpoint mapping of the control system. So let us from now on fix definitely an initial point x0 and a final time capital T. So the endpoint mapping in time capital T from x0 is nothing else but the C1 mapping that maps a control U to the final point x U of T, of capital T, of the trajectory solution of the control system corresponding to that control U and starting at the point x0. With this endpoint mapping, of course, the reachable set in time capital T from x0 is nothing else but the image under the mapping E of the set of controls. Let me recall that a control is said to be regular, and in that work we call it strongly regular, whenever the differential of the endpoint mapping is surjective. And at the contrary, a control is said to be weakly singular whenever it is not strongly regular, which means that the range of the differential of the endpoint mapping is a proper subspace of Rm. And of course, the first immediate result and well-known result is that whenever there is no control constraint, that is, when capital U equal Rm, if a control U is strongly regular, then by the implicit function theorem or by the open mapping theorem, it follows that the endpoint mapping is locally open, and hence, of course, XU of capital T belongs to the interior of the reachable set. So this is a property of local controllability. Well known, it's the implicit function theorem. Also, a useful characterization of weakly singular controls is the following. A control U is weakly singular, which means that the range of the differential of the endpoint mapping is not equal to the whole Rn. It is not surjective. If and only if the trajectory X admits a non-trivial weak extremal lift, which is exactly the contents of the well-known Pontryagin maximum principle. It says that there must exist an adjoint vector, a non-trivial adjoint vector, denoted by P, such that the triple XPU satisfies the Pontryagin equations. So X dot is equal to dH over dP, P dot is equal to minus dH over dx, and also the condition dH over du is equal to 0. Here it is dH over du equal to 0 because there is no constraint on the control. And so this characterization as being an extremal is equivalent to the weak singular property of the control. It is equivalent. Now, what happens whenever we add some control constraints? Well, the situation is also well known, of course. Let us first assume that U is convex. And now we define the concept for a control of being strongly U regular. It means now that it is not the full range of the differential of the endpoint mapping, but you see the image under the differential of the endpoint mapping of the tangent cone to U. The tangent cone at U to the set of controls that are now restricted to take their values in the convex set capital U. So it has a tangent cone. And so now we slightly weaken the property of surjectivity of the differential of the endpoint mapping. We restrict it to the tangent cone at U. Okay, so this is the property of being strongly U regular. And the contrary, we say that the control is weakly U singular whenever it is not strongly U regular. That is when the image under the differential of the endpoint mapping of the tangent cone is a proper subcone, proper convex subcone of Rn. And now, still by the implicit function theorem, but now we need an implicit function theorem with constraints, because we have now a set of constraints on the control. So we need what is called sometimes the conic implicit function theorem, which implies in the same way as before that if U is strongly U regular, then the endpoint X of capital T belongs to the interior of the reachable set under control constraints, right? So nothing else again, but an application of implicit function or conic open mapping theorem. Okay, you can notice that, of course, strongly U regular implies strongly regular, but also the converse is wrong. As you can see on this also very simple example in 1D, where I can sum up why the converse is wrong by saying when you have some control constraints, then just take, let's say, a bang-bang control. That is a control that is saturating constraints. Then in general, such a bang-bang control will be strongly U regular, but it will be weakly U singular. Sorry maybe for those words, but we need many words in order to describe the situations. Also, the Pontryagin maximum principle gives a characterization of weakly U singular controls in terms of extremal lifts. And there also it is completely classical. Control U is weakly U singular whenever the trajectory X has a non-trivial weak U extremal lift. That is, there exists an adjoint vector so that the Pontryagin equation are satisfied. And this time we replace the condition dH over du equals 0 by a condition with a normal cone to the set capital U. That's all. That's the only modification. And now, third case, the case of general control constraints. It is also the classical situation. All of that is reminders. We say this time that a control U is weakly U regular whenever, so this time the condition is even weaker, the Pontryagin cone of U is equal to Rn. And at the contrary, we will say that U is strongly U singular whenever it is not weakly U regular. And let me recall what is the Pontryagin cone very shortly. It's also a very classical notion defined by Pontryagin and his PhD students some 70 years ago. The Pontryagin cone at U is the smallest convex cone containing all variations vectors. So what is a variation vector? It is based on the classical concept of a needle-like control variation. Let me recall it briefly. A needle-like control variation is a specific kind of, let's say, L1 variation of a given control. You are given a point omega in capital U, a positive real number alpha, and you define that variation of U that you can see here. You do not change the control U except along the short interval t plus alpha, where you impose to the variation to be equal to the constant omega. This is a so-called needle-like control variation. And it is well known that this concept has led 70 years ago to a very general proof of the Pontryagin maximum principle. And what is now the variation vector? So the variation vector is this W here. It is the unique solution of the variational system, df over dx times W, with this initial condition. And actually what can be easily checked, it is at the basis of the proof of the Pontryagin maximum principle, is that if you make this finite difference, this is the endpoint mapping evaluated along the needle-like control variations, and you make the difference with E of U, you divide by alpha, it is the finite difference. Then as alpha tends to 0, you recover exactly the variation vector at time capital T. So it is it was an important added value for proving the Pontryagin maximum principle, because it is not exactly the usual strong differentiability of the endpoint mapping that would be in L-infinite topology. Here, saying something quite wrong, we would say that it is a kind of L1 differentiability of the endpoint mapping, although it is not exactly that, but okay. And with that concept of weakly U-regular control, we have the following proposition, saying that if U is weakly U-regular, which is until now the weakest possible regularity property that we have defined, then the endpoint X of capital T belongs to the interior of the reachable set. And there also, to prove this statement, it is not difficult, it is quite classical, and we just apply the Conic implicit function theorem to a kind of endpoint mapping restricted to needle-like variations. Okay. You can also notice that when capital U is convex, strongly U-regular implies weakly U-regular. So let me repeat that this regularity property of the control is the weakest one that we have defined until now. It is also the most possible general. And as well, we have a characterization for a control of being strongly U singular. And this time, this is the full, complete general Pontryagin maximum principle, U is strongly U singular whenever, if and only if, the trajectory admits a non-trivial strong extremal lift. That is, there exists an adjoint vector so that the Pontryagin equations are satisfied with the most general maximization condition of the Hamiltonian. Okay. Now that I have defined all these and recalled these notions, let me come back to the main issue, that is robustness of reachability under control sampling. So I have defined in the last slide the main assumption of our theorem, which assumes that the control U is weakly U regular. So let me recall that it means that the Pontryagin cone at U is equal to the whole Rn. And it is under this main assumption that indeed we find that reachability in fixed time capital T is robust under control sampling. In this sense, there exists a threshold such that for every partition of norm sufficiently small, less than this threshold, the point x of capital T, it's x1, I should write x1 here. x1 is still reachable under under sampled controls. And this property, we call it PC unif. This is in contrast with the property below, that is PC, where you would exchange exactly the quantifiers here, which is a weaker property. Okay. Yeah, that's it. So we the remark here is that we may have the weaker property PC while the stronger property PC unif fades. For instance, let us take the very easy example in 1D. You take the simple dynamics x dot equal U. You take the set of control constraints U equal to 2 points, 0 or 1. That is, you allow the values of controls only being either 0 or 1. Now you define that control written here, U equal to 1 on the interval 0p, 0 on the interval p4. Then it is easy to check that this control is weakly U regular. It's a bang-bang control, right? Regular enough. The target point x1 equal p is L infinite U reachable, right? Also, we can notice that x1, it's again x1 here, also belongs to the interior. It belongs to the interior of the L infinite U reachable set. However, the strong property PC unif is not satisfied. It's very easy to understand. It is just because if you take a partition involving only rational sampling times, then due to commensurability rigidity, you cannot reach x1 with controls that are piecewise constant over such a partition. So here on this example, we can see well that PC unif is not satisfied. However, it can be checked that PC is satisfied. So in passing, let me observe that the property of belonging to the interior of the classical reachable set is not enough in order to ensure robustness under control sampling. Maybe this is not so much intuitive, but you can see it well on this simple example. Also, another remark is that for this example, the control set is kind of trivial. And in particular, it's not convex. But even if you assume that capital U is convex, you can cook examples even where the target belongs to the interior of the reachable set, but it does not belong to the PCTU reachable set. So also with U convex, you really need the property of being weakly U regular if you want to ensure the property PC unif. And the last remark on the assumptions is that you can slightly relax the convexity assumption, but not much. You can relax it to the property that capital U be parametrizable by a convex set, which is almost the same. I mean, up to some mapping, to some C1 mapping, U is convex, and that's all. And if you try to relax the property of being connected, then in general, the conclusion fails. So this is why I have written here that our assumptions are almost sharp. Now, let me comment on older existing results. And mainly, I will shortly comment here on the remarkable series of works that have been done by Hector Sussman, Eduardo Zontac, and Kevin Grass quite a long time ago. It was in the 80s and 90s, but mainly in final time. Actually, Sussman has much focused in the 80s on the PC property, not on PC unif, on the PC property. And this is why I introduced this property. Actually, the initial idea by Sussman, which was very remarkable, was written in a paper in a Journal of Differential Equation in '76, where Hector Sussman introduced the very relevant notion of, and well-known notion of, normal reachability. What it means is that you assume that you have reachability under piecewise constant controls, but with an endpoint mapping whose differential is surjective. So exactly with that concept, with that kind of concept of regular control that I introduced before, because thanks to surjectivity of the differential, you can use the main tool that is the open mapping theorem and finally obtain robustness of normal reachability. And thanks to that relevant notion of normal reachability, Sussman, in a series of papers, proved in particular the following striking result, that if you assume that a system is globally controllable, which is a strong assumption anyway, but you assume that the system is globally controllable in free final time, then your control system is also globally normally controllable as well. Meaning that every point, every target point can be also reached from a given initial point with piecewise constant controls, also with the surjectivity of the differential of the endpoint mapping. But their result is in free final time, not in fixed final time, because in fixed final time, by the way, this result would fail. And also in a series of papers of Sussman with Zontac, they investigated sample data global controllability, but still in free final time. And I will just mention quickly that probably the most refined result was due to Kevin Grass, who was a former PhD student of Hector Sussman. It was written in MCSS 92, and Grass was very much interested in the property of small-time local controllability that was mentioned by Karine Bouchard on Saturday morning in her talk. And Grass proved that under a very weak assumption, non-tangency property that I could comment, it's a very weak assumption that is always true, for instance, for analytic systems. Then small-time local controllability is equivalent to sample data small-time local controllability, and it's also equivalent to being small-time normally self-reachable. And this was a very important theorem by Grass that permitted to Grass and Sussman to conclude on the very interesting issue of being reachable by what they called nice control. Nice control can be, for instance, a piecewise constant control, or maybe an analytic control or polynomial control, etc., etc. It was a very, very nice series of works. And do I have 2 or 3 minutes, Pier Marco?
Yes, yes, sure. Yes, you have exactly between 2 and 3.
Okay, thank you very much. Let me motivate why, with Loïc Bourdin, we have investigated these robustness issues. Our main objective, actually, which is an ongoing objective, is to investigate the following problem. You consider a general optimal control problem, given in a very general form, nonlinear, and still in finite dimension. Now, on the one part, you consider it with what we can call permanent or classical controls, okay, for which you can apply the PMP, the Contre-Gain maximum principle. And on the other part, you consider it within the class of sampled data controls, that is the class PCTU, where also you can get an optimal solution, and you can also apply a less known version of the PMP on sampled data controls that we derived with Loïc Bourdin several years ago in MCRF. And as you can guess, our natural question, a natural objective, is to try to show that whenever the norm of the partition, so the steps of the subdivision, tend to 0, you would like to be able to ensure that the optimal solution there, the optimal sample data solution, does converge in a strong sense to the continuous, to the permanent optimal solution. This is the objective. And indeed, so in a theorem that we are finishing to write, we prove that this objective is true under several assumptions. The 2 first assumptions are very classical assumptions under which we can ensure existence of classical minimizers, nothing deep. And the 2 last assumptions, which in particular that one, we assume that the optimal solution has a unique normal extremal lift, which are, let's say, generic assumptions. And the key steps of the proof, in order to prove the convergence property, is to use the assumption 4, so to use this regularity property, in order to ensure robustness of reachability under control sampling. And this is here that we had this main motivation in order to explore that issue. Okay, this is so this is one key lemma in the proof of that theorem. And let me finally end my talk by mentioning in passing, as a particular case of that study, the famous case of the famous linear quadratic case. So what is linear quadratic? It is when the system is linear and when the cost is quadratic. In that case, it is well known that in the classical setting, you can use Riccati theory. So if you are in fixed finite horizon, you can use the classical differential Riccati theory that, by the way, with Loïc, we have extended to the sample data context by deriving a sample data difference Riccati theory. And maybe more interesting, in the infinite horizon case, so if you are trying to perform, for instance, regulation objectives, so in that case, the matrices are autonomous. You are in the classical case of the algebraic Riccati equation. Then we have proved recently with Loïc the commutation of this diagram. I mean, either you can perform a sample data Riccati theory over a finite horizon. We call the solution ETT, like here. Then you can let capital T, the horizon of time, tends to the infinity. And what we show is that we recover, as you can imagine, ET infinite, which is what we have called the sample data algebraic Riccati solution. And also, in both sense, we can let the norm of the partition tend to 0. And in that case, it is exactly what we can expect. Here on the left, we recover the classical solution of the differential Riccati equation. And here, when capital T is equal to plus infinity, we recover the usual algebraic Riccati solution. So we have a complete diagram. And I will stop here. Thank you.
Thank you. Thank you, Emmanuel, for this very interesting talk. And let's see if anybody in the audience has questions or comments.
Can I ask something, Pier Marco?
Sure, Enrique.
So, Emmanuel, does this have this result, this analysis, has any impact on other properties like, for instance, star pike or others?
I think that you can you recover some turnpike issues, for instance, in this diagram, Enrique, because let us see, for instance, this classical arrow here, this classical convergence. So I just say that the usual solution of the differential Riccati equation over a finite horizon of time 0 capital T does converge, but I have to say in which sense, to the usual algebraic Riccati matrix. So to be more precise, E sub capital T is a matrix depending on time, small t, belonging to 0 capital T, and the convergence that is true is the following. You give me any time small t positive, non-negative, and then if capital T converges to plus infinity, then E sub capital T of small t converges to E infinite. And actually, this convergence is even uniform over any compact interval of time. And this is actually exactly what we can call a turnpike property, because it means that this convergence is true except at the end of the horizon of time.
Okay, thank you. Thank you.
Okay. Enrique and Emmanuel, what about numerical application of these results? One would imagine that in perspective, this should give some hints.
Yeah. Actually, Pier Marco, this is exactly what we have in mind. This is an important motivation is to plug this general question here in the more general context of full discretization schemes. When I say a full discretization scheme, I mean not only discretize the control, as we do here finally, but also discretize the state.
Mm-hmm.
And there, it is already known that in general, we do not have such a nice convergence issue. And this issue has been very much investigated by people like William Hager, for instance. And William Hager showed some kind of 20 years ago that if you use a symplectic Runge-Kutta scheme in order to discretize the state, then in some sense you recover a commutation of a diagram. And this is exactly that question that with Loic we have in mind for the future. We would like to fully understand it.
Okay.
Okay. May I add a comment on this?
Sure.
Can you hear me?
We cannot hear you.
You can hear me now?
Yes.
No? May
Yes.
I say something? Okay. So thank you for the talk. I have a comment regarding the application of this kind of results to numerical methods. Well, in fact, if you think about a time discretization where you have a sampling that is related to a time step delta t, you have to investigate exactly in that direction. But there is also another technical point that I think should be investigated. Instead of asking for an exact reachability with respect to points, perhaps you should have a neighborhood of that point of radius epsilon and see if the discrete system can enter that neighborhood. Because from the numerical point of view, asking to reach a single point, which has measure 0, is not very helpful, because in practice, I mean, you will never be able to do that with a numerical scheme. What you can do is to enter a neighborhood of that point.
Yeah. So what you mean is very relevant, Maurizio. What you mean is investigate the question of robustness, maybe not of, let's say, exact controllability, but of approximate controllability. Yes. Yeah. And indeed,
what you can reach is a neighborhood of a point.
Yes.
Perhaps you can let epsilon go to 0, but from the numerical point of view, I mean, finding exactly a point in the space, it's impossible. Unless you have compatibility condition with respect to delta t, delta x, and very special dynamical system.
Yeah, it's very relevant, Maurizio. And indeed, strangely, by the way, there already exist a number of results, mainly due to Enrique's Zoisois, in the infinite dimensional setting, I mean for linear PDEs, where Enrique investigated in a long series of papers the robustness of controllability under discretization for heat equations, wave equations, and so on. And without entering into details, what Enrique could notice indeed is that robustness of approximate controllability can sometimes be ensured, while robustness of exact controllability cannot. So it's a softer notion, which is, of course, very, very interesting for practical issues. I agree. But until now, here in that context, we have not investigated that property yet.
Okay,
but
thanks.
I agree with you. It's an issue that has to be investigated for sure.
Okay, thank you. Thanks to everybody for this discussion, and especially to our speaker. And so, virtual applause. And let me continue with this morning's program and with our next speaker. Thank you. So our next speaker is Camille Pushol from University of Paris. Camille is a young researcher. He's met the conf at his university. He got his PhD in 2018, so very recently, in fact, from Labo Jacques Lilians, having as his advisor. He works on optimal control, inverse problems, and especially interested in applications to biomedical sciences. And the title of this talk today is, as you see, Unwanted Sparsity for Linear Inverse Problems with Non-Negativity Constraints.
Thank you, Marco. Thank you. And thank you for the invitation. So I will be speaking about a series of works that I've done with Olivier Verdier, who's from University of Bergen in Norway. And as you can see, this is about, say, simple inverse problems. They are linear, but with the specificity that they have non-negativity constraints. And especially I want to speak about sparsity, about these problems, and I'll explain why this is unwanted sparsity. Okay. So the setting, let's say the simplest example you have to have in mind is the following. So you have a linear model, here a matrix with non-negative coefficients. This is very important. And you measure some data y, which stacks m measurements. And you want to solve ax equals y. So the simplest setting would be you do that through least squares. But here you want to recover a non-negative vector x. This is very important. And in my talk, I will actually look at the more general setting where you want to minimize a divergence between y and ax. And here D can be a very general divergence. So it's not a distance, not necessarily a distance. It must split as a sum of atom-like small divergences, D. And I'm just asking that the divergence satisfies the separation property and some basic regularity assumptions, essentially convexity, with respect to the second variable. And I'll explain why this is relevant for applications to indeed go to more general divergences and not merely L2 norm square. And in fact, the goal of my talk is to pass the continuum for such problems. Meaning, I do not want to look at what happens at the level of a vector x, but instead at the level of a functional space. So now x has become mu, and the notation mu is a bit telling you a bit more for what's to come. So we're looking for a suitable functional space to work in, and we want to look at non-negative functions of that space. And let me insist that the data is still finite dimensional. So I passed the continuum in the unknown space, but we're still measuring, and that's probably closer to what happens in practice. You have m measurements, and from that you would want to recover some image. We'll see that's the idea. So why image? The key kind of example that we'll have throughout is the example of positron emission tomography. So positron emission tomography, I don't have enough time to enter the details of how this modality works, but it's a medical imaging modality. Lots of scans that you can do are positron emission tomography scans, which I will call PET in the rest of the talk. And it happens that if you write the statistics of this and the physics of this, essentially, you end up with the fact that you get in each detector, there are a certain number of detectors in PET. So yi is the number of points that you've detected in the detector I. These are photons which are detected. And you can prove, and there's some assumptions on the physics, that the number of measurements, the measurement vector y is distributed as a Poisson random variable with mean a mu. And mu here is a measure, it's a radon measure, say on some compact K, a non-negative measure, I should say. So K is the compact on which you want to reconstruct the image. And A acts on mu through, so the i's component of the vector A mu is given by the integral of AI against the measure d mu. And if you write so what you want to recover is mu, the image. And if you write the maximum likelihood problem for this, actually the negative log likelihood problem for this, you end up with this minimization problem. You want to minimize the divergence between the data y, the measurements, and a mu over non-negative measures mu. And this is exactly of the form that I had on the previous slide, if I can manage to go back. Okay, that's exactly that form. With the specificity that now we have fixed some functional space, namely that of non-negative measures. And here, the divergence that comes into play naturally due to the statistics is the Kullback-Leibler divergence. So this does not satisfy the triangle inequality, it's not symmetric, and that's how it's defined. Okay. Okay, now I want to explain why we want to go into continuum. So for those who work in inverse problems, it's quite natural that when you look at the discretized version of an inverse problems, then at some point you want to write things in continuum to really understand how ill-posed the problem is. You want to look at some compactness of the operators involved. So it's quite natural. And in fact, in the specific case of medical imaging, especially in the case of PET scans, when you go to do a PET scan, so next time you go for a PET scan, look at what image you get. So let's imagine this is, of course, a toy example. On the left, this is the image that you're supposed to reconstruct. You put that through a PET scan, you get some data, and then you try to reconstruct. So believe me, here we're using some algorithm which is intended to solve exactly this problem, this minimization problem. And what you end up with after 100 iterations of that algorithm is an image that's fine, looks okay, but there are some pixels that start to take over the image. So here I've zoomed on the image, and there's one pixel. So overall, the red part is at 3 here, and there's one pixel which is at 6. So trying to show himself, and actually, if you keep iterating, this pixel or some others will take over the image, and you'll typically end up with this, what you would interpret as a sum of Dirac masses. And now there's a last motivation, and as usual in research, it was actually our initial motivation. So I'm a bit lying when I say we want to go into continuum for understanding the oppositeness. What we wanted to do, and I think I won't be speaking about this because of time, but I think it's interesting to have that in mind, is we wanted to look at the case of movement. So now imagine you go through a PET scan, and what you're trying to image is your lungs. So it's a pity, but you breathe, so your lungs will be moving, and you want to correct for the movement of lungs. And one way to model that, and it's getting more and more popular in the medical imaging sciences, in the imaging sciences in general, is to model that through diffeomorphisms. So certainly you don't want to discretize things, because diffeomorphisms do not preserve grids. So you really want to write things in continuum and then maybe to discretize. So that was our initial motivation: write things in continuum, use diffeomorphism, then maybe discretize for practical applications. Okay. And then I just point to one article on the subject of movement related to this. Okay, so we want to investigate the sparsity phenomenon related to this, and now maybe I can say what I meant by unwanted sparsity. Certainly, you want to reconstruct an image that will look reasonably smooth, so you don't want Dirac masses. When you go to image your lungs, you don't want Dirac masses going out of the scan. And it happens that the right functional space to take is that of Radon measures. Maybe you're convinced already. And actually, you can check that for simple cases, which are actually unrealistic, the minimization problem that I've written leads to optimal to Dirac masses. So if you try to write this in Lebesgue spaces, this is ill-posed. The infimum is you've got an infimum and not a minimum, because you have actually Dirac masses as minimizers. And as I explained, for PET scan, this is completely natural. Actually, I didn't mention, but the statistical model has one key object behind it. It's a Poisson point process, and this is defined by a Radon measure. So in some settings, it's completely natural that you want to work in a measure setting. Okay, some state of the art on this. So some people have tried to write this, especially the Kullback-Leibler case in continuum, but they work in Lebesgue spaces. So as I just explained, they miss something, because it could be that you have an infimum. So they end up having various restrictive hypotheses on the operator A, which counteracts this, but this is not very satisfactory. There's another work which went a bit unnoticed, but which found this key idea of working in measure spaces, but does not really elucidate, just remarks that in some cases you can have discrete measures, how general the phenomenon is, namely, should you expect Dirac measures often or not? I would also want to mention sparse super resolution. So it's a completely different field where the aim is not to recover something smooth, say your lungs, but some spikes. You're looking for stars. You have some imaging modality. So you know that the unknown is a sum of Dirac masses, and you want to recover discrete measures. So it's a very different context, but here also people tend to work in measure spaces, because this is what they want. And the typical set of questions that we look at is the generality, again, of this sparsity phenomenon that I've hinted at in the simulation slide. So sparsity is something completely exceptional. Is it really, is it due to how you solve the minimization problem, or is it inherent in the minimization problem? Is it specific to some cases, some divergences, to some operators? These are the questions that we've tried to tackle. Okay, so let me go back to the minimization problem, and so we want to minimize the divergence between the data y, what you measure, and a mu over non-negative measures mu. So here A is some linear operator which maps non-negative measures into Rm, and the definition it does that by the ith component of a mu is the integral of a certain function ai against d mu. And the hypothesis is that AI is a non-negative. This is what happens for applications in this setting. And also that the AI functions are continuous. And this is the case for PET, for instance. And the examples I have in mind also always satisfy that hypothesis. But we'll see that maybe you don't want to ask much more than continuity. Okay, the key object, and it might not come as a surprise, is the following cone. Now you can look at all the possible a mu's you can get through the operator a, mu ranging over non-negative measures. And this will be playing a key role in what follows. So you can write the optimality conditions for this problem. So you have to be a bit careful because you're in finite dimension. There is a bit of a lemma about how you identify the normal cone to non-negative measures, but nothing quite fancy. You just end up with these optimality conditions, necessary and sufficient. The problem is convex here. So a measure is optimal if and only if a certain linear combination of the AI functions is non-negative everywhere, so non-negative on the whole compact, but vanishes exactly on the support of the measure. And here lambda star is some dual variable which lives in Rm. It's a vector in Rm. So there's one situation where essentially these optimality conditions are useless. Is the case where the data that you ended up with is in the cone. Then essentially solving the minimization problem is, if you're in the cone, it means that there is some measure mu such that a mu equals y, and namely the divergence of y and a mu 0. And being optimal means exactly solving a mu equals y. So if you're in the cone, this is what you want to do. So the minimization problem is not so interesting. You just want to find solutions to a mu equals y. When things get interesting is when you're outside of the cone. So if y is not in the cone, then the optimality requires not equivalence, but requires that the support of the measure is included in the zero set of some function. Some linear combination of the AI functions, and now the lambda i's, some of them, at least one of them, must be non-zero. Because you're not in the cone, if you look at the fact that lambda is a dual variable, you are certain that one of the lambda i's is non-zero. So it could be that this function is non-trivial. So the support of the measure is in the zero set of a possibly non-trivial function, and then we have to investigate more precisely what may happen. And the first sparsity result you can get, it's a quite straightforward one from these conditions. So recall that if you're optimal, there's a dual variable which tells you that the support of the measure cannot be in anywhere in K. Also recall what I just said, namely when for some reason the optimal measure mu star you've obtained did not manage to match the data yi, the measurements in the ith detector, then the dual variable lambda I star must be active. It's non-zero. Then you get the obvious following result. If you're not in the cone, in which case this will happen at least for one I. This is a definition of not being in the cone. And if the family, it's completely obvious from this, if the family AI is analytic and linearly independent, then all optimal measures are discrete. This function is non-trivial because of linear independence, and it's analytic, so you end up with discrete measures. So this is the first sparsity result that we obtained, and really relies almost directly on the optimality conditions. So is this result enough for what we have in mind? Not really. Why is that? Because the analyticity condition is very strong. in many imaging problems, and this is the case of PET, for instance. So in PET, typically you would have one detector here which links Z4 and Z5, and another detector here linking Z0 and Z1. And then the corresponding function AI has its support, including in the orange region. And the compact is the whole polygon here. What this means is there is no way that the functions are analytic. They are non-negative and they are compactly supported inside K. So this is certainly not satisfactory an assumption, and we need local properties to go a bit further. Okay, so this is where the second sparsity result comes in. So we have to lower the hypothesis we make on the functions AI. We need less regularity than analyticity. So we will have to strengthen our assumption on the divergence T. In the previous result, I was assuming essentially nothing on the divergence. And now I'm going to restrict my attention to some divergences. So what we could prove is that, again, assuming that Y is not in the cone, if some, at this stage, rather abstract condition holds on the divergence, and I'll explain in a second why this comes into play. And you can think of the Kullback-Leibler divergence, which does satisfy this, but the L2 norm square does not. That's important. Then if the family AI is no longer analytic and linear independent, but locally, so locally analytic and locally linearly independent, essentially it means that on their support, the AI functions are analytic, and local linear independence is you just restrict linear combination to the functions that are active on the set you're looking at. So I won't give the full definition, but this is kind of intuitive. Then all optimal measures are sparse, not discrete, but sparse. And what's interesting is you can somehow explain where sparsity arises. To be more precise, whenever I is such that you've not managed to map A mu star to the data Y, then on the support of AI, the optimal measure must be singular. So will be supported in a lower dimensional set than RD, the compact set where the compact set lives. And a few words about the proof. So actually, this is where the assumption on the divergence comes in. It's very important. Is that what you really want to be able to say anything is that whenever you have this, whenever yi is not a mu star I, you want to make sure that there is some mass on the support of AI. And this is what this assumption does. It tells you that whenever there is, so the converse tells if there is no mass on the support of AI, then it means that necessarily here you had equality. And this is the assumption that you need. And then combining the fact that you know now that there is mass on support of AI, and this is a previous result that holds in full generality that the lambda I star is non-zero, the dual variable is active, then you can study what happens locally on the support of AI and end up with this result. Okay. Okay, then one natural question we had was, we have this local linear independence and analyticity condition. Does typical functions satisfy this assumption? So analyticity is not too difficult to check, but linear independence can be really complicated, especially if you look at 2D, 3D problems where the geometry gets really involved. So let me just give one toy example where things are kind of, you can kind of understand what happens. And it is reminiscent of typical things you would get in higher dimensions and for applications. So typically in higher dimensions, you would get some basis functions and you would get some easy transformation of these functions that you would define the AIs. So one way to create this in 1D is you consider a polynomial of degree k, which is non-negative on some interval AB, and then you extend it by 0 elsewhere. So this is the polynomial, and you just shift it all over the real axis. So you shift it once with a certain shift size. The shift size is fixed, and you keep on shifting it an infinite number of times, and you just look at the functions on a certain compact of R. Then here, that allows you to go to linear algebra and find dimension. You can prove that if the degree of the polynomial is high enough compared to the inverse of the shift, that indeed the functions generated by this approach are locally and locally analytic. This is obvious, and locally linearly independent. Okay, this is one toy example, and then we conjecture that for example, in the case of pet function on the circle, we conjecture that local linear independence holds true as well, but we don't know how to prove it just because it's very technical. Okay, so as you saw, the key question is, are you in the cone or not? The cone C. When the data is outside of the cone, the results that I've presented show is that you expect sparsity. You should have sparsity. So I should at least have a few words about what this means to not being in the cone, what not being in the cone means. In fact, most models that give rise to this optimization problem, they involve a dispersion parameter. So previously, when I wrote the statistical model for PET, it was Poisson, but I didn't include this dispersion parameter phi. For instance, in the PET case, phi is related to the time you're exposed, meaning that the scan is being taken. So the longer you wait, the better the image will look because you will register more data. And in fact, for most models, noise models, you have this property, which is usually just some kind of law of large numbers that says that the measurements that you get y, this is a random variable, tends to a mu r, where mu r is a real image, as the dispersion parameter goes to 0. So, and it's quite natural. The less noise you have, the less likely you are to be in the sparse setting, y not in the cone. So you really have to think about this situation, why not in the cone, as being a noise condition, a high noise condition. Okay. And now I think I have still a few minutes. I'll just mention, because I've focused on when things go bad, namely you're not in the cone, you get sparse measures. 5 minutes, okay, thank you. So another natural question is, can you at least say that things go well if you're in the low noise regime, namely if you're in the cone? And this is a difficult question. This is the subject of the next slide, but let me just mention, even in the case where you focus on one specific example, say the Kullback-Leibler divergence example with the PET case, there's one algorithm that is used when you go for a PET scan, actually variants of that algorithm, is the so-called Mlem algorithm. This is the following one. The formula itself is not relevant here, not very important. But you might wonder now, imagine that y is in the cone, so in the favorable case, if you iterate with this algorithm, do you end up with a measure that's not sparse? Do things go well, at least in this case? And to answer that question, there is a general answer, a general hope, rather. So recall that trying to solve the problem when you know that when you assume that the data is in the cone is equivalent to trying to solve a mu equals y. And there's a theorem of Georgiou, which is actually from a completely different context, so it's quite interesting, which tells you the following. If you're in the interior of the cone, then there is a smooth measure solving this. Here, smooth means having a density with respect to the Lebesgue measure. Doesn't tell you that all measures are smooth. Actually, there will be measures which have singular parts, but at least there is at least one. And now the question is, in practice for a given problem, does your algorithm select one of these smooth measures or a bad measure when y is in the cone? So what we could prove with Olivier Verdier is that, for example, for the case of PET and for the typical algorithm that's used in this setting, then things go well. If you're in the interior of the cone, in which case by the result above, you know there is a smooth measure solving the problem. And if you start from an initial guess which is smooth, then all the cluster points here, the weak star cluster points of the algorithm will also be smooth. So at least we can kind of certify that things go well in the low noise regime, which is satisfactory. And the idea of proof is kind of nice. There is a nice property of the Mlem algorithm that you can prove namely that along the iterates of the algorithm, you will approach optimal measures in the sense of the Kullback-Leibler divergence. Here, this is a Kullback-Leibler divergence between measures, not between vectors. And some regularity properties of the divergence allow you to conclude here. Okay, and I'll just end up with one or two slides of simulations, and then I'll stop here. Just telling you, we also looked at a more pragmatic question of, now let's imagine you've recovered data from a given scan or whatever problem you have. Can you somehow try to know if you should expect sparsity? And sparsity, as we've seen, is essentially an independent notion of the divergence. It really reduces to, do you have Y in the cone or not? Which is also equivalent to this. The minimization problem has a minimum that's positive or that is 0. If it's 0, then you're in the cone. If it's positive, then you're not in the cone. And one way to do that, to look at this problem, is to be very pragmatic and try to solve the minimization problem, so which depends on the divergence. And along iterates of the algorithm that you have, try to say, oh, I'm in the sparse case or not. And this can be done by weak duality. So I won't I just explain in a few words, and I'll stop here. So by weak duality, the function d of y a mu is always above the dual function. And if for some reason you are able, and in what we did, we explained a bit how to try and do that. If you are able to come up with a lambda, a dual variable, such that this function is positive, then that's it. It means that there is no way the minimum of this problem is 0. You cannot go below this g of lambda. This is what we call a dual certificate of sparsity. And whenever you find such a lambda, then you've just proved that y is not in the cone. And this you can try to do along iterates to define a lambda k that depends of your algorithm. And then you can, so I think I'm lacking time, but you can actually in practical case, for instance, this is the one what we had earlier in the presentation. I can certify here that you're outside of the cone. At this stage, after a certain number of iterations, I can say y is not in the cone with this methodology, which is, I think, an interesting kind of approach. And sometimes it's really just we cannot manage to certify. We don't know if you're in the cone or not. Okay, so I'll stop here. These are some references about my talk. Thank you.
Okay, thanks. Thank you for your talk. Interesting. And let me ask if anybody has questions, a short question, maybe. Okay, well, if not, well, we'll leave time for questions to pop out during the coffee break, which is going to start soon. So thank you again, Camille. And
thank you.
So we'll now we have a virtual coffee break, and we'll resume at 11:40.
Yeah. Okay, we'll start 11:40. Thank you, Professor Cannassa, for this activity as chairman. Then we will start 11:40. The next chairman will be Professor Masahiro Yamamoto, and the next two speakers will be Martin Duga and Michael Intermuller. Thanks for all.